we can start without any further overdue. The second talk will be Katharina, talking about Lipschitz continuity of diffusion transport maps. Okay.
Thank you very much for the invitation. It is really a pleasure to be here. So I will mainly talk about the joint work with Giovanni Conforti, which is already on arXiv, but I at least want to add a teaser in the end on the extension that we are working on together with Louis-Pierre Chaintron. So let me set the stage. The title already indicates a little bit what is the goal. The goal is that given two measures on RD, so let me denote them probability measures, which have densities. So rho should have a density which is proportional to exponential to the minus u with respect to the back measure. And nu should be a certain log perturbation from it. So it also has a density which is proportional to the exponential minus w of, and if this is the density with respect to it. And you should imagine rho to be a very regular measure, like a Gaussian, for example, and we want to construct a map M, so that it's a measurable function from RV to RV, which transports a rho onto unit. And moreover, it should be Lipschitz. Ideally with a Lipschitz constant that is independent of the dimension of the underlying space. And we will see right away why. So why could this be interesting? I want to give a very simple example, namely essentially the fact that you can transport rho in a very regular way to nu should kind of transport also certain nice analytical properties to nu. And for example, this is the case for functional inequalities. So let us just do the simple computation in the case of the Poincaré inequality. Why I said it, transport. So let us suppose that we have a Lipschitz transport map, and suppose that rho satisfies a Poincaré inequality. Oh, sorry, I forgot to say it. But if there are any questions, don't hesitate to interrupt me. For example, is this notation okay for everyone, or do we need a precision? No voice means it's okay. Essentially, what is the Poincaré inequality? If I take a suitable test function, which has mean 0 against rho, so I take an f, which f the rho is equal to 0, and I'll compute the squared norm with respect to rho. It will be bounded by a certain constant, which is the Poincaré constant by the coordinate squared Lipschitz. And once we have a Lipschitz map, this property immediately translates to nu. So let us just take, the proof is very straightforward. Let us just take a test function such that its mean with respect to nu is 0. By the push forward property, also f of m, the rho will be 0. Right? This because these two integrals are equal by definition of the push forward. And then I can just verify the Poincaré inequality for nu. So let me take this test function here. Since m pushes forward relative mu. This is the same as the integral of f concatenated with m squared d rho. Now, this is an admissible function for my Poincaré inequality, so I can apply my Poincaré inequality to this function, and I obtain that this is smaller or equal than the Poincaré constant. I apply the chain rule, and I get that this will be, I'm a bit sloppy with norms on RD and operator nodes, so please forgive me that I only do one bar every time. So this will be by the chain rule smaller or equal than gradient m times gradient m squared 0. And now, if my map M is Lipschitz, I can brutally bound, I can apply Cauchy-Schwarz and brutally bound this gradient of M by the Lipschitz constant of M. So I get that this is smaller or equal than CP norm. Let me just write it like this, all times squared, integral gradient squared 0. And to finish, I just use that mu is the push forward under of rho under m to obtain that I get a Poincaré inequality for mu. Okay, so this is very powerful, and this computation also shows you why we are interested in getting as sharp bounds as possible to transfer these functional inequalities. And you see that this does not only work for Poincaré, I just use it as an example. So the search for these transport maps is, well, due to this motivation, and it has initiated essentially in the year 2000 when Caffarelli proved the famous Caffarelli contraction theorem. So essentially, the first approach to look for these transport maps was to look at optimal transport. Optimal transport is a variational problem, selecting an optimal map in a suitable way. It is not important how it is selected, but you had some structural properties, and one could prove regularity under certain assumptions. So this was the first approach. It was looking for maps coming from optimal transport. I don't write the definition because we really don't need it today. It is nevertheless a very seminal work by Caffarelli, which says that if your rho is the Gaussian, it's in a simplified form. If you suppose that rho is the Gaussian, your distribution, and your nu this time is of a form, not a perturbation, but exponential minus v with respect to the back, which is uniformly log-concave, so we can have a lower bound on the Hessian in terms of eigen ordering of matrices. So the lowest eigenvalue is bounded by alpha, which is positive. Then the Caffarelli contraction theorem says that the map coming from optimal transport, let me call it M opt, M opt will be 1 over square root of Caffarelli. So in particular, if your measure nu is even more log-concave than the Gaussian, your optimal transport map is even a contraction. So this is very powerful, but unfortunately, it only allows for measures which are very, very regular. And in the past years, there has been very few progress on proving regularity of optimal transport maps because they are minimizers of a variational problem, and it's very difficult to prove regularity. There are also many counterexamples when you cannot hope for it. And so around the year 2010, 2011, Kim and Milman have proposed to choose a very simple model from physics to construct transport maps, namely, I think I don't okay, 10. I think it got published at 11. And the idea is you take the Langevin dynamics, which is the overdamped Langevin dynamics, and under certain conditions on your invariant measure, the Langevin dynamics converges to the. Okay, let me write the equation. So your invariant measure will be the nice measure rho. So the drift term will be gradient u. Okay. The idea is that intuitively you will start in your irregular measure, which is mu, and following the Langevin dynamics should encode a transport as t goes to infinity to, so you start in mu, and you follow the flow of mu t, and as t goes to infinity, if your invariant measure is nice enough, you should converge to rho. And you know that usually you look at the Langevin dynamics at the particle perspective in the form of the following SDE. So usually the corresponding particle follows this stochastic differential equation with x0 following the law of mu. And so in order to define a transport, we kind of have to switch our particle perspective to a deterministic one. And moreover, we want to transport from rho to nu and not from nu to rho. So we also have to invert this process somehow. And the way we are going to do it is we first have to rewrite our equation as a pure continuity equation so that we see that instead of having the probabilistic particle perspective, you can also view this equation. So you can also have a deterministic particle perspective on this equation. And for this, we do the simple rewriting that like this. You can interpret the Laplace term also as a transport term by writing it as the divergence of the gradient of log of mu t times mu t. And you see, just as passing from this particle perspective to here, the gradient u generated this transport term, and usually the Brownian motion generates the diffusion. But now we have this also as a transport term. So we have this nonlinear transport vector field, which is log of mu t, which transports it as well. And we will do one more rewriting of this. Namely, if you keep in mind that the mu t, it's a big slope. Is there a question?
I'm sorry. Well, if I find this identity in one dimension, so the gradient should be the derivative, and then when I differentiate the log, I get 1 over mu l, and so I get gradient of 1, and that gives me 0 and not adaptation. I mean, I'm a bit confused because I've never seen that identity, and so.
Okay. So the gradient of mu t is.
Because like if I do it in 1D,
yes,
gradient is the derivative, and then I differentiate the log, so I get 1 over mu whatever it is t.
I think it may be a problem of the parentheses. The gradient of log mu t, if you differentiate it, is gradient of mu t over mu t. You agree?
Yeah.
And then the mu t, so it's a very formal because I assume it to be positive.
Oh, okay.
But it cancels, and then you get the divergence of the
Thanks.
gradient. Yes.
Yeah.
But good to know that. Okay. Actually, if you're a bit familiar with optimal transport, you can interpret this kind of as a Wasserstein gradient of the entropy. But
but I'm not familiar
Okay,
with
okay.
too
But
much of so
for
maybe
us,
that's why.
for us here, it's sufficient that the computation works out well and that we can do this computational trick, which seems a priori not very useful, but will be crucial for our formulations. Now, if you keep in mind that these mu t are actually the radon-nicotine densities with respect to the Lebesgue measure, and this here is also the, so let's do it, let me write it. This is also essentially the gradient of the, so minus actually, minus the gradient of the log of the radon-nicotine density of a rho, right? Because a rho is exponential minus u. And so I can just put the logs together and I will arrive that my Langevin dynamics can be written as a pure continuity or a transport equation, however you want to write it, with this with the following vector field, which is the gradient of log of the radon-nicotine density of mu t with respect to rho. And then I have to reach. Okay. And now I can do the same thing as I did before at the particle perspective, and I see that if I define my particles to follow the following ODE, at this point everything is still formal. It follows minus gradient log d mu t over the rho. Obviously now it's very nonlinear because it already depends on the overall distribution. And I let x0 start in u, then my essentially the same computation as before gives that the log of xt will be equal to mu t. Okay. And now let me just do a last rewriting of this because I want a map. I want to get a map from this particle system. So let me just define the following family of maps. ST, which map from RD to RD. I require S0 to be just the identity map, so mapping X to X. And then I require ST to satisfy the following ODE. This is the same. Let me maybe give a name to this. This vector field will be now the gradient of the potential function Vt. So with the minus. Yes. So let this family of functions follow this following ODE. And then you see that okay, now you see that I have more of a probabilistic mind, but I will write both. So if my initial distribution now, let me call it y. So if y is distributed according to nu, then by construction, st of y will follow the distribution of mu t. Okay, you see clearly that it's true for S0, and then you just follow the fact that we have constructed the ODE in a way that it gives a certain particle perspective on the Langevin dynamics. Or if you wish to come back to the transport, we have that ST pushed forward nu is equal to mu t. And to follow the picture, now, if everything goes well, and it will go well under the hypothesis I show you later, S infinity will, there will exist a limit for ST, and it will push forward the initial condition to the stationary distribution, which is rho. And moreover, we can invert S infinity. and finally get the transport map from the nice measure to the initial measure. So M will push forward rho to nu. So this was the construction by Kim and Milman. They initially did it for the case when U was x squared, so only for the Gaussian or Ornstein-Uhlenbeck process. And since then, there have been a lot of works trying to understand which conditions on U and on the initial measure can you impose in order to obtain a transport map, which is Lipschitz continuous, ideally independent of the dimension. And to see what you need to prove, okay, deep line is not ideal for me. Let me just cite a small lemma that is by Nicolinsa and Schenfield, I think from 3 years ago. And maybe before stating the lemma, so what we have for the construction of ST is we know that it follows this SDE. And we want to show that it is Lipschitz, right? So essentially we want to show that the gradient is uniformly bounded. And so you can guess if you derive this ODE, if you want the gradient to be uniformly bounded, or then you need some estimates on the Hessian of VT. And this is essentially exactly the lemma. Let me just write it. So suppose that we can bound the Hessian of VT from below by lambda min, and from above lambda max. And then the map we are interested in is Lipschitz continuous with constant, which is exponential in the integral of the lambda min. So it is the exponential of minus integral of from 0 to infinity of lambda min. And since we can always ask also about the other direction, S infinity will then be Lipschitz continuous depending on the upper bounds of the eigenvalues on T. So Lipschitz continuous exponential infinity lambda max. Okay. And the proof follows essentially by what I told you. You derive this equation, you apply you use the bounds that you have on the Hessian, and you apply a Gaon one. Yes.
Maybe a stupid question, but how do I know these things are finite?
Nothing is clear at this point. Of course, this is all formal. I will provide you a hypothesis soon, but I prefer to first do the construction of the map. But you're absolutely right. The most difficult part is to prove that these are finite, and that especially integrable. Okay. And this is where, so to give you maybe an idea of the first proofs on proving that these things are finite, people have always used this deterministic particle system and have played around with it. And what we are going to do today is we might use this deterministic particle system to construct the map, but let us not forget that this comes from very nice large line dynamics, right? I really want to use the stochastic interpretation of this problem to get regularity. And this is what we are going to do. So for this, I'm going to use, so for people who know this, I essentially have a Hopf-Kohl transform here. So I can expect the Hamilton-Jacobi-Bellman equation to appear, or a control problem. And this is exactly what we are going to do. So let me recall that all we want now is to bound the Hessian here. So let me just, for convenience, define my phi t a function phi t. People doing control are very familiar with this notation to be my time-dependent potential V, time inverse. So T is a finite time horizon. Okay, maybe I should write it. And I just repeat the definition. This is the minus the log of, now it is the mu big T minus small t over the rho. I think rho was my inversion. Yes. And so now you could brutally derive this property to see which equation it satisfies. And it turns out that if you derive phi t in t, phi t will satisfy the following Hamilton-Jacobi-Bellman equation. Okay, let me get the, sorry, this the partial derivative in time of phi t plus the Laplacian minus gradient u times gradient phi t minus 1/4. Okay, and this is really a non-trivial computation that you have to do at some point. Usually I don't have time to give more intuition on it, so if you want to know more, ask me in the end. I think the only identity that is quite here is that at the terminal time, we know exactly the value of phi t because it will be the minus the log of the density of the initial measure, so it will be equal to W, because W was the log perturbation of a rho. And again, sorry, I still didn't give any assumptions, and I'm already halfway in the talk, but we will get there, I promise. We can also, and this is exactly what I indicated, we can have a stochastic representation of this phi t in terms of a stochastic control problem, hence the Hamilton-Jacobi-Bellman equation. Namely, it is equal as the infimum of the expectations of the integral from t to t s squared over 4. So you minimize some kinetic energy because your dynamics that you're following are essentially the Langevin dynamics corrected with a certain control. So now you have Langevin dynamics which are corrected by a certain control. You start in t in x of the Weill function, and you have the terminal condition here. So if you wish, this is kind of a stochastic control, a stochastic representation of a nonlinear PDE, just in the way as you can represent the semigroup also by the expectation of something. But because this PDE is nonlinear, you have an optimization problem behind. And it essentially tells you that the value is given by minimizing the kinetic energy in competition with the terminal conditions, which was our initial condition. And the way you correct it is by correcting the drift term. I wanted to say one last thing. Under the assumption I will tell you, there's always an optimal control, and it has a very nice character. It is given by minus 2 times the gradient of phi s evaluated at xs, where xs is the optimal dynamics. By the way, I have some funny constants here, and this is just because I chose the Laplacian and not 1/2 of the Laplacian. So it's nice for the transport map to take the Laplacian, but for the probabilistic perspective, you get some funky constant, but they don't change anything. Okay. Now that we have this representation, I will use probabilistic techniques, more precisely coupling techniques, to prove regularity of this function, more precisely Hessian estimates, because once I have the Hessian estimates, we win. And I think now is the time that I should start telling you what are my assumptions, under which all of this computation can be made rigorous, and under which I can actually get finite lambda values. So, okay, the first assumption is we need our potential U, which is the confinement potential, to be confining in some sense. And classically, in people, what you would expect is that you expect your potential to be uniformly convex. This is for sure sufficient, right? And this is also usually the assumption under which most of the results of Lipschitz transport maps exist. So let me just write a certain definition of Lipschitz, uniform convexity, which is that if you evaluate the gradients in scalar product against the difference of the vectors, it should be bigger or equal than alpha times x minus x squared, where alpha is positive. So what we managed to do with the techniques that we have is we managed to relax this constraint a little bit by not imposing a uniform. You can relax this constraint by requiring a bound that is not uniform in all x and x hat, but rather depends on the distance of the point. And this will be a function kappa u of the distance of the point. And I want my potential to be confining enough. So instead of requiring it to be strictly positive everywhere, so this is the same inequality, I just require not anymore a uniform bound. What we will require is that when the points are very, very far, I want my potential to be confining. So in notation, if I take the radius between the points far, it should be strictly positive. And moreover, but this is a smaller technical condition, it should not behave too badly around zero. So the potential should not be so concave that the potential becomes repulsive when points are close. And this is encoded in the following integral condition. So the integral of r times kappa u negative part of u should be integral. So this is just to be completely correct. Essentially, imagine it to be not too repulsive enough when points are close. So just to give you an example, for example, in this class of functions, you can choose u to be the double well potential. So something like this is allowed, as long as when the points are far, you're convex. In the middle, it can have some non-convexity parts that are doable. And the intuition from the particle perspective is if you have like diffusion particles, when they are far, your potential should help meet the particles. But when they are close, they're kind of as being on a compact, right? And so the diffusion should be enough for them to meet. So you don't need the potential to have an attractive part. Furthermore, so the assumptions I give you now are of perturbative nature. So I allow W should be, okay, so obviously U should be C2, sorry. If we want to be completely rigorous, and W should be C1. I think we can do less, but I will talk about it. W should be Lipschitz continuum. So I am dealing with log Lipschitz perturbations of a potential that is attractive enough. And I need a slightly more, there are certain variants of what I need slightly more on U. to get my Hessian estimates. Let me just give one of them. I think I want the eigenvalues of my Hessian of U should be uniformly bounded. So U should be, I don't know if you allow me to write it like this. By this, I just mean that not M. So all my eigenvalues of U should be the Hessian of U should be bounded. There are alternatives, like you can also ask the Hessian of U to be Lipschitz or something, but you need slightly more than one to conclude. Okay, first, under these assumptions, all the computations I have shown you are rigorous, all these manipulations, the control formulations, and so on. It can be proven. What is left is to really see that the lambdas are finite. Okay, and for these, we first make rigorous that. No, I will here. So under 1 prime, one can prove that the Langevin dynamics are exponentially contracting by using coupling techniques. So what I mean by that is, if you consider two solutions of your SDEs representing your Langevin dynamics, I will leave some space because I will add control later. You can construct a coupling, and this comes from the work of Andreas Eberle from 2016, where you have two coupled SDEs representing the same dynamics, just starting in different points. Let me also already start in T, just because for the control I will want to start in C. And the crucial part here is that all I can play with to compare these two solutions at the particle perspective is to choose two different Brownian motions. And this is exactly what we are going to do. So if you take two different Brownian motions, I will explain you the construction in a minute. Then, if B hat is chosen suitably, you can prove that there is an exponential contraction in L1 up to a constant, namely, you can prove that the expectation of XS minus XS hat, L1 norm, is smaller or equal than a constant times exponential of minus lambda S minus T X minus X, where lambda, so C and lambda are positive constants, which depend on this convexity profile here that I have introduced. The idea is to construct this second diffusion is to make rigorous what I told you before. So when particles are very, very far, when particles are very, very far, the drift component will make them closer together because we suppose that it is convex. It looks like a convex function when particles are far. When particles are close, my potential will not attract them. But since I have two different diffusions, the diffusion will make them meet. So essentially, if you have your particle xt and your particle xt hat, the way you construct the Brownian motion, the second one is, so suppose you have the Brownian increment in this direction. Then the way you define the second Brownian motion is you define the second Brownian motion to be reflected along the plane which is orthogonal to the difference vector. So you will, if your Brownian increment goes in this direction, the Brownian increment of B hat will go in this direction. Okay, so and this should help the particles moving together. Now, every probabilist will tell me, no, but okay, you drew the picture well, like with probability 1/2, they will approach each other, and with probability 1/2, they will actually go away. And this is true. This is why there's this constant C before, so there's still some work to do to make the parts that move towards each other count more. There's a whole technical construction. You need to switch a little bit, change a little bit the geometry of your space, but it will be equivalent to L1 up to a constant factor, which is this constant C, and you will get exponential contraction in this way. What is important is, because of this phenomenon that only with probability 1/2 they get closer, you only get this contraction in expectation. So you will not get it almost surely or something. And now, there were a lot of preliminaries, but we can finally start proving regularity of VT to get the Hessian bounds. And we will use this coupling construction and prove that if your dynamics are contracting, this will translate to regularity of phi t. Okay, and for this, let me modify the coupling a little bit. Namely, now I will not look, obviously, I have the stochastic representation in terms of this control problem. So I don't want to couple Langevin dynamics. I want to couple the optimal control, the stochastic processes from the optimal control problem. And so I will add a well-chosen control. I will add the gradient of 2 times the gradient of phi s here in the dynamics. Okay, blue is almost the same color. I hope it's okay. So now my first particle is, by construction, the optimally controlled process for phi t x. And for my second SDE, I will actually choose the same control now. So this is just, you will see why in a minute. And so you should keep in mind that this here now will be an optimally controlled process, and this here will just be an admissible control process. Again, there is some work to do to prove that this is really admissible and so on, but we will need this, and we will kind of copy the strategy of how to use coupling to prove regularity of a semigroup, but now in a nonlinear fashion for this control problem. And maybe I should do a statement. So now what we are trying in our first step before moving to the Hessian estimate, we prove that phi t is uniformly Lipschitz under the assumptions I showed you here. And the way we do it is we can now compare phi t evaluated at x hat minus phi t evaluated at x.
So you use the same drift with excess in both?
Yes, I use the same control. Here, the potential still depends on, here it depends on x hat and here on x, but I use the same control because when I now do the difference of the value functions, my kinetic energy will cancel. So the difficulty here is my dynamics already depend on the gradient of the value function, which I know qualitatively it exists and so on, but I have no quantitative information so far. And I want to get quantitative information. And so the easiest way is that I pick the same control so that when I now take the difference here, it will cancel. So by construction, my second process is an admissible process for the control problem. So phi t x hat is smaller equal than my expectation. Let me write it. gradient. So here, okay, maybe you don't see the blue really, but let me. Okay, no, it's gonna stay white. And this is really an Excel. So this is this part here estimated using the fact that X hat is an admissible process from my control problem. I get an inequality. It is not necessarily the infimum. For the second one, I have chosen the optimally controlled process. And so I know that this is equal to minus the expectation of the same integral. And now I really benefit from the fact that I have chosen the same control. Technically, you can also use epsilon optimal controls and so on, but let's just use the optimal one. And the you get the terminal cost, which is W of X. And you see that this is the whole reason we use the same control. This is an object we don't know how to control yet, but it cancels. It's the same. So the whole thing is equal to just the difference of, because there's a minus, the difference of the W. I can use that I chose my W to be Lipschitz continuous, and it will be smaller than the gradient. Okay, this is just to write the Lipschitz norm times the expectation of the L1 norm of xt minus xt. And then you see that to conclude, I now want to use my contraction estimates from that I get by having chosen this coupling, to get not only a Lipschitz bound, but also a Lipschitz bound which is decaying. So keeping track of all of the constants more or less, I get that this is more equal than the Lipschitz constant of W, C. I get exponential minus lambda t minus small t x minus. And you see that I have proven in one direction that the bound for Lipschitz continuity, I can just exchange the role of x and x hat, exchange the coupling and I get that I have a uniform bound on the gradient of phi t given by this constant u, which is even decaying exponentially as t moves away from big T. Okay.
So for the coupling constant, the coupling estimate, you use only the regularity of the trajectory with u. And the fact that you have the same drift in both, you can apply Eberle proof. There's no problem.
Yes.
So
yeah, good. That's a very good point. So that's another reason why I've chosen the same. The Eberle proof works because it only works on the difference process, and the difference process does not see if I add the same control. This is a very good point. Yeah, I didn't say it, but at first the Eberle proof was correct only without control, and it is correct because I add the same process twice. And here I only have an estimate on the difference process. And the difference process doesn't see if I add 2 times the same. Okay, let me just call this constant. Okay, just to be sure, how much time do I? 10 minutes, right?
10-ish.
Okay. So, but this happens almost every time that we will not see the Hessian estimate. This is also wrong. This is a constant depending on the difference. And to get back to your question, now from this estimate, we actually get now, not only we get a Hessian Lipschitz estimates of this phi t, but we also can conclude that now finally, I should have checked for colors before, this whole drift will satisfy my 1' assumptions. because in particular, if you look at the definition I have given you, this will be satisfied also by U, which are of the form U uniformly convex, sorry, not very formal, but plus Lipschitz function. Okay, because if you look at the definition of the kappa, if you have your U of the form uniformly convex plus Lipschitz, as the points, okay, let us maybe just do the computation. Uniformly convex will be, okay, A, Lipschitz will be B. If you do the computation here now, gradient of A plus B minus gradient of A plus B exact. Obviously, they're differentiable. I suppose them to be differentiable. This will be smaller or equal than I use, there's the minus. I use that my A is uniformly convex, so this will give me alpha x minus x hat squared. Then I brutally bound the gradient of B by its Lipschitz constant. So I get the impact of 2 times gradient B times x minus x hat squared, and I have to divide. Okay, I hope this is okay. So I bound, the first part is just uniform convexity. So I use linearity of the scalar product. And then the first term just comes from the fact that my A is uniformly convex. My gradient of B, I just brutally bounded from below by its, I use Cauchy-Schwarz, I use brutally bounded by its Lipschitz constant. And I get that actually it will be gradient of B times x minus L1 norm of Euclidean norm of x minus x hat. And to get it in the shape that I want here, I see that my kappa in this case is of the form alpha plus, minus 2 gradient B T over R. And so you see that as R is big, I am convex, particles get attracted. As R is small, I only have this integrability condition to verify, and it's okay, because the R cancels with this R. And so why do I tell you this? Because one of the most important consequences of this estimate now is that my optimally controlled drift now enters in 1 prime. So yes, let me write it here. From the Lipschitz estimate, we obtain that my kappa of U plus 2 times phi t. Okay, so this is now really my potential driving the control dynamics. The optimal ones is bigger or equal than kappa U of R plus I called it no, should be minus, sorry, 2 times the Lipschitz constant of T over R. And so in particular, I get that now my optimally controlled dynamics are also contracting in the sense of the coupling construction by Eberle. And then essentially, it becomes more technical to iterate the argument to prove now the Hessian estimates. Essentially, what you do is you derive an equation for the optimal drift. And you see that if you can prove that this thing here is kind of Lipschitz continuous, you win. So you will get that phi as Lipschitz. And you see from this proof that actually we get that uniform bounds on the Hessian from both sides, which are decaying very well in time. And these bounds, they are all explicit in the paper. It's just a nasty computation. And it will turn out that both the lambda min and the lambda max will be integrable under these assumptions. And this is essentially the conclusion. Now, if you allow me 2 minutes, I know it was very technical, but I just wanted to say I'm a few weeks too late on the current project with Giovanni and Louis-Pierre, because we are just recently on, I mean, it's been ongoing for a while, but things happen. What we are currently doing is, you see that from the construction, okay, maybe it's less fast than I thought, but the kappa here, sorry, I really want to mention it, but maybe it is too much. The kappa here can also be seen as an integrated profile of the Hessian. So it is also the infimum of the integral of 1 over r integral from r of the Hessian of u. I think you take the minimum over all x of okay, then I have to cheat words. I probably didn't even write it. No, okay. It is kind of, don't take me too serious on the exact constants here, but it's essentially what I want to say is there should be a theta somewhere. So, probably here. Okay, don't take me too serious on this one. I am getting a little bit tired. What I want to, the point I want to make is that kappa of u is also kind of a lower bound on an integrated convexity profile, so on the Hessian. And what I just wanted to say is that if you take the lim in are going to 0 of kappa u, you will actually go towards the lower eigenvalue of the Hessian of u. Okay. And so what we are currently investigating is, instead of using all this machinery to prove two-sided bounds, we've seen that we only need one-sided bounds, right? And so what we are currently, since the kappa, the convexity profile encodes the lower bound, which is exactly what we're interested in, it makes sense to look whether the function in time, sorry, of kappa of u plus 2 phi t satisfies some equation. And it turns out, and then I leave you, that if you take the function let me be sloppy, I am interested in the function of kappa times r. It turns out that using coupling by reflection and a little bit a modified strategy, you can prove that this function here satisfies a Burgers equation, which is quite remarkable, right? It is, and it is essentially the derivative of the Hamilton-Jacobi-Bellman equation. And using this Burgers equation, and this is why it's not the main part of the talk, even though it's very interesting, I realized last week, we can prove that the map M that I've shown you from the Gaussian, so rho is really proportional to exponential minus x squared, well, prove any new let me call it u, to any u satisfying 1 prime is Lipschitz continuous with a constant that is really not that bad. Okay, this is. With a constant that is independent of the dimension. So essentially, and I'm sorry, I really wanted to tell you this, but I was short. But I just at least wanted to add the teaser for the preprint that's going to arrive soon, where we really can construct Lipschitz map to any of these asymptotically convex problems. And with that, thank you for your attention. Yes.
So I'm wondering if, so this situation that you just mentioned, the recent progress corresponds to the case where U is quadratic and W has some quadratic growth.
Mm-hmm.
Can you do this for a general U? That is to say, you have W that is of quadratic growth and U satisfying some one-sided bound under convexity.
Okay, so mean you replace the Gaussian by a U?
Yeah, value.
Mm-hmm. And you asked me what you can reach.
Yes.
Yeah. So what is really interesting, I am not sure. The answer is I am not sure, because what I needed here was that what you call the reciprocal potential is uniformly convex for this to work. And as of now, I only know it to be true for Einstein-Uhlenbeck.
Okay.
So the reciprocal potential is up to a sign. I don't know if it's minus or plus the Laplacian, something like this in some constant. So this object here has to be uniformly convex. And obviously, if you, no, there's here. If you take U to be the Euclidean distance squared, this will be the case. So this is where it breaks. If you find another U satisfying this, then it's possible. If you have less conditions on this one, I'm not sure. I would have to check.
And is your Burger's equation a sort of an integrated version of the equation that is considered by Hamilton? So the equation by Hamilton is just that in your HJB you take formally second order derivative of everything.
You just take the first derivative, and
Okay.
it is exactly this Burger's equation.
Okay.
Yeah.
Okay.
More questions? Okay, if not, let's thank the speaker again. To avoid a conflict with the lunch, let's resume at 11:50. Okay. There are some drinks there too.
I have one more question. So what is, isn't, from my point of view, absolutely not